Section 1.9 talks about compositions of matrix transformation. So from section 1.8, we left out few tables. Now, anytime you need those standard matrices, I will provide. So for example, if you want to reflect about the x-axis, you simply take the y and replace it by a negative. That means a point in quadrant 1 will become quadrant 4, and the other quadrants will match accordingly. And if you apply T sub E1 and E2, you end up with this standard matrix. Those matrices are provided. You don't have to memorize them. Reflecting about the y-axis, there it is. So if you multiply any vector or a matrix by negative 1, 0, 0, 1, that would reflect that about the y-axis. You want to reflect about the line y equal x multiplied by the following matrix. Now this carries to 3D. We're going to focus mainly on your homework on 2D. Some of the examples I do will be 3D, and those are provided as well. That's not a big secret. And that's how all of these work. Orthogonal projection along the x, along the y, and rotation. If you want to rotate in a clockwise manner, so basically positive rotation like you do in trig, you multiply a vector by the cosine or the sin when the angle is given, and that does it. That rotates about the origin, the certain angle that's specified. So this is a theorem defining the composition. It says if TA runs from Rn to Rk and TB runs from Rk to Rm, so they have to match. The range of the original must be the domain of the range of that the range of the original must match the domain of the next transformation. So if I take T sub B composition with T sub A, that would be simply the matrix BA, where B is the transformation on B and A would be the transformation on A. Now the composition with T sub B and T sub A denoted by TB composite with TA is the process of direct transformation from Rn all the way to Rm. And it looks like this traditionally in math, but if you look at it, so A maps X into T sub AX, that's a matrix A, and we talked about that in the previous section. The linear transformation on B will be simply a matrix B. You could bypass that and simply run T sub B composited with T sub A, and that will run X from R sub n all the way to R sub m one shot. Now it turns out to be really interesting how the inverse work. If we're talking about a transformation, oops, wrong key, here we are. If we're talking about transformation on inverse, so let T sub A be transformation from Rn to Rn, whose standard matrix A is invertible. Then we say that the transformation on A is invertible as well, and if you want to take the inverse of the transformation, that's simply the transformation on the inverse matrix. Remember, these are matrices, so the outcome of those is a matrix. So we start off with a bit of practice of how this plays. Determine whether the operation T1, T sub 1, and T sub 2, T sub 1 and T sub 2 commute. See if the composition is commutative. Now we know from before that that's not the case. Sometimes it is if it's a special case. Here they're saying on number 2, T sub 1 is a transformation, R sub 2 to R sub 2 is the orthogonal projection on the x-axis. The orthogonal projection on the x-axis, so T sub 1 is simply 0, 1, 1, 0. And T sub 2 . is the orthogonal projection onto the y-axis. So that goes 1, 0, 0, 0. Actually, I copied that one wrong. This is 1, 0, 0, 1. Not no 1. It's zeros. And this is 0, 0, 0, 1. Projection on the x, projection on the y. Projection on the x would be, where was it? Right there. Projection, okay, one only in the first and one in the last. Let me make sure I got this right. Yep, I got them right. So let's see how this works. Well, we want to figure out what is the composition of T sub 1 composite it with T sub 2. If I take T sub 1 composite it with T sub 2, well, that is T sub 1, T sub 2, and that's simply 1, 0, 0, 0, and 0, 0, 0, 1, and let's see what that is. That is 0, 0, 0, and 0. If I take T sub 2 composite it with T sub 1, I'm looking at, oh boy, come on. That will be T sub 2, T sub 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, that's 0, 0, 0, and 0. So in this case, they match. In this case, it seems you could switch them. And if I look at B, rotation about the origin with respect to pi over, so T sub 1 is cosine of pi over 4, negative the sine of pi over 4. Again, that's in the table. Sine of pi over 4 and cosine of pi over 4. So it's basically rad 2 over 2, rad 2 over 2, negative rad 2 over 2, and radical 2 over 2. Now, T sub 2, reflection about the y-axis. About the y-axis, that would be reflection about the y-axis for 2 dimensions. Reflection about the y-axis. Okay, it's right there. That will be negative 1, 0, 0, 1. That will be negative 1, 0, 0, 1. Well, in this case, again, if I take T sub 1, composite it with T sub 2, that would be T sub 1, T sub 2. That's simply rad 2 over 2, negative rad 2 over 2, rad 2 over 2, rad 2 over 2. And if I multiply that by, I'll get negative radical 2 plus 0, okay? 0 minus radical 2 over 2. For the bottom, I'll get negative radical 2 over 2 and radical 2 over 2. And if I was to go ahead and figure out T sub 2, T sub 1, that will be T sub 2, T sub 1. T sub 2 is negative 1, 0, 0, 1. T sub 1 would be radical 2 over 2, negative radical 2 over 2, rad 2 over 2, and rad 2 over 2. And that would be negative radical 2 over 2, radical 2 over 2 plus 0, 0, radical 2 over 2, and radical 2 over 2. And in this case, they don't match. Here, T sub 1 composite with T sub 2 does not equal T sub 2 composite with T sub 1. Now again, after this chapter, we're just going to come back to those and use them. instead of just doing busy work. Well, let's see how this works. On number 4, let's say T sub 1 is a reflection on the xy plane, but that's for R3. xy, so you want z to be 0. And T sub 2 is pretty much 2x 3yz. Well, what is that? That is 2 0 0 0 3 0 0 0 1 multiplied by x y z. So basically, that's the matrix of transformation. So if I really work this out, that's my T sub 2 matrix of transformation. Now, if I take T sub 1, composite it with T sub 2, I'm looking at 1 0 0 0 1 0 0 0 0 and 2 0 0 0 3 0 0 0 1. I'll end up with a 2 plus 0 plus 0, okay? And here I'll get a 0 and a 0. For the second, I'll get 0 plus 1, that's 0. I'll get 0, the 3 remains, and a 0. And for the third one, since it's 0, it's going to give me all zeros. And if I look at the other transformation, let me give myself a bit of space. If I take T sub 2, T sub 1, that is 2 0 0 0 3 0 0 0 1, and a 1 0 0 0 1 0, 3 zeros. That would be 2 0 0, that's a 2, 0 for the second, 0 for the third, then a 0 for this, and I'll get a 3 and a 0, and the last one will be zeros as well. So here T sub 1 composite with T sub 2 is identical, and to doing those forward or backward, that wouldn't be an issue. All right, number 4. So hopefully you're getting really comfortable with this. Find T sub. So here they just tell you plane. You just want to get used to all of these notations. They say this is what? This is AB. This is BA. That is T sub B, T sub A, which is simply BA. And that is BA. Let me put A right there. 6, 3, negative 1, 2, 0, 1, 4, negative 3, 6. So I'll get 24 plus 0 plus 16. 24 plus 16, that's 40. And then I'll get 0 plus 0 plus a negative 0. Oh, wait. I'll get, for the second, 12 plus 0 minus 12, that's a 0. Negative 4 plus 0 plus 24, that's 20. For the second, I'll multiply by the first, negative 6 plus 10, that's 4. 4 plus 8 is 12. And then I'll get negative 3 plus 0 minus 6, negative 3 minus 6, negative 9. And I'll get 1 plus 5 plus 6, 12, 12, 17, 18 altogether. And I go for the last one. I'll use that row right there. With the first 12 plus 32, 12 plus 32. So 12 minus 6, that's 6, plus 32 is simply 38. I'll take 6 plus 0 minus 24. 6 minus 24 is negative 18. And negative 2 minus 3, that's negative 5. Negative 5 plus 48, that's 43. All right. And they want me to do T sub AB, T sub AB, T sub A composite it with T sub B. That is the transformation of A, transformation of B. Well, guess what? That's simply AB. And that one we would put them in order as we see them. So AB, this first, then that. We're looking at, let's see how that works. First one, 24 minus 3 is 21. 21 minus 2 is 19. Then I go for 0 plus 50. That's 15. 15 plus 3 is 18. And 6 times 24 plus 6, 30. 30 minus 8 is 22. Obviously, those are not equal. If I look at those, right? Oh, they just say find the standard. They're not checking if it's equal or not. Now to find the second, I use the second. That will be 8 plus 0 plus 2, that's 10. I'll get 0 plus 0 minus 3, that's negative 3. And I'll get 8 plus 0 plus 8, that's 16. And for the third, I use the third. That's 16 plus 3, that's 19. 19 plus 12, 19, 30, 31. And 0 minus 15 minus 18. Minus 15 minus 18 minus 33. Yeah, it is 33. And if I take 16 minus 6, that's 10. 10 plus 48 is 58. And there it is. Again, we just want to get used to knowing this transformation. It's really represented by a matrix. If I look at number 8, and number 8 has few parts, find the standard. So we're talking about R2 in this case. Rotation about 60 degrees. That followed by an orthogonal. Okay, so T1 is pretty much the cosine of 60 negative the sine of 60, sine of 60 degrees and cosine of 60 degrees. That's simply 1/2 radical 3 over 2 negative radical 3 over 2. And T sub 2 is simply a reflection about the line y equal x, y equal 1, 0, 0, 1. Again, that's from the table. Oh, I messed up. That's T3. There's a middle one I skipped. If I look at T sub 2, followed by an orthogonal projection on the y-axis, on the y-axis, and on the x-axis, oh boy, I got him. I was trying to memorize him. X-axis, x, y equal x, we got it right idea. And x-axis, that will be not reflection, projection. Projection on the x 1, 0, 0, 0. Yeah. And then the y will be okay. So what do they want us to do here? Well, a rotation about the x-axis followed, so rotation about the y-axis. The total transformation will be transformation 1, transformation let me check. Right. Transformation 1, you apply first, then you apply, transformation 2, then you apply transformation 3. So basically, you're going to have to really put those in order. And we're going to start with T sub 1, which is 1/2 negative radical 3 over 2, radical 3 over 2, 1/2. And T sub 2 is 1, 0, 0, 0. So let's see what we get. If we multiply this out, we get 1 over 1/2. And negative radical 3 over 2. For the second, we get 0, and then Since we're using that, we're going to get zeros. And don't forget T3 comes next, 1, 0, 0, 1, and that would be 1 over radical 2. So, okay, I'm getting the answer and it's not matching. That's because I wrote this wrong. This is 0, 1, 0, 1. Oh boy. So that's going to change this. I'm like, wait a minute. I'm looking at the answer. I have that in front of me. 0, 1, 1, 0. Okay, so when I multiply those, I'll get 0 plus 0. That's 0, 0, 1/2, and negative radical 3 over 2. And that will be the transformations of those in that order. Now, if I look at part B, an orthogonal projection onto the x-axis. Projection onto the x-axis. So T sub 1 is 1, 0, 0, 0. That's the first thing you do. Then T sub 2 reflection about 45 degrees. Well, they're all radical 2 over 2, and I know only one of them is negative, that one. Because sine and cosine of 45 degrees is radical 2 over 2. And T sub 3 is pretty much reflection about the y-axis. About the y-axis, negative 1, 0, 0, 1. Okay, and if we want to figure out the total transformation, in order we apply T1, then we apply T2, and we apply T3. And we know from the previous exercises that we did for homework that those are commutative as far as multiplication, as long as they are written in this order. T sub 3 is negative 1, 0, 0, 1. T sub 2 is radical 2 over 2 for each except that one is negative. And T sub 1 would be 1, 0, 0, 1. Again, any way you would like to do this, that is possible. So let's work it out. I don't know, you could do it left to right if you wish. If I run this left to right, I'm looking at negative radical 2 over 2 plus 0. That's radical 2 over 2 plus 0. So 0 radical 2 over 2 and negative 0 radical 2 over 2 multiplied by 1, 0, 0, 1. And that will yield negative radical 2 over 2 plus 0. Okay, and oh, no wonder that was a 0. That will make that 0, 0. Okay, that will make that negative radical 2. That will make that radical 2. That will make that a 0, and that is, man, I keep on. Again, I provide those for you. You don't have to memorize them, but if these were zeros, then okay. So I get, okay, that one is fine. And third time will be a charm. So that was correct. I'll get radical 2 plus 0, radical 2 plus 0, 0. I'll get radical 2 over 2 and radical 2 over 2. And if I multiply that by, there we go, I'll get negative radical 2 over 0, and then 0 plus 0 is 0, radical 2 over 2 plus 0, and 0 plus 0 is 0. There it is. That's the total outcome of those three transformations applied in that specific order. Now, part C. So this pretty much describes all of this. A rotation about the origin by 15 degrees. Okay, T sub 1 is you rotate 15 degrees. T sub 2 followed by a rotation of 105 degrees, followed by a rotation, so all of these are rotations of 60 degrees. So if I take T, that is T3 composited with T2 composited with T1, right? And the net effect of those would be, let's see, 15 plus, if you add those, that's a 10. The total transformation of that would simply be 180 degrees, which means T is simply the cosine of 180 degrees negative the sine of 180 degrees, sine of 180 degrees, and cosine of 180 degrees. Well, at 180, we know those two are zeros. That's a negative 1, and that's a 1. I meant negative. All right. Now, consider the following transformation. So, this was 8. Yeah, we're skipping that. Again, we really want to get used to those. So if I take T sub 1, it's 3 dimensions. That is simply 4x1 negative 2x1 plus x2 and negative x1 minus 3x3. Or simply the matrix for that would be 4, 0, 0, negative 2, 1, 0, and negative 1, 0, negative 3, operating on x1, x2, x3. Oh, that's x2, not x3. So that is so I could say T sub 1 is simply that matrix. Now, of course, I don't need to write all of this. I could figure this out quickly. For example, for T sub 2, if I really want to figure out the outcome, I know that T sub 2 is simply, well, look at T sub 2. 1, 2, 0, 0, 0, negative 1, 4, 0, negative 1. And just to make sure that you know where this comes from, so you list them out, x1 plus 2x2, negative x3, and 4x1 minus x3. And, you know, the list goes on. And you list them out, 1, 2, 0, 0, 0, negative 1, and 4, 0, negative 1. And that's really how you find those. It's not even that much work. But if I want to find T sub 2, T sub 1, well, that's simply T sub 2, 1, 2, 0, 0, 0, negative 1. Remember, the transformation is just a matrix. And if I take the top one, that is 4, 0, 0, negative 2, 1, 0, negative 1, negative 3, 0. And that would be 4 minus 4 plus 0, that's 0. That will be 0 plus 2 plus 0, that's a 2. 0 plus 0 plus 0 is a 0. 0, 0, 1. 0, 0, 3. And 0, 0 plus 0 is 0. And for the last, 16 plus 1 is 17. And 0 plus 0, that's a 3. And then the last one, all zeros. There we go. And if I want to go the other way around, if I want to go T1 composite it with T2, well, we're going to go T1, T2 first, swap those, and here we will get 4 plus 0, 0, that's 4, 8, 0, 0, 0. For the second, I'll get negative 2. I'll get negative 4 plus 0 plus 0 is negative 4, and 0, negative 1, 0 is negative 1. Negative 1 plus 0 is negative 1. Negative 2 plus 0 is negative 2. and 0 plus 3 plus 0 is 3. There it is. And again here a T1 and T2 cannot be interchanged. And for the last one, just to get a really good feel how this works, we want to take T1 composite it with T sub 2. Well, T1 composite it with T sub 2 of x1, x2, x3 will be pretty much the remaining matrix, and we take T1, T2, it's right there. We'll get 4x1 plus 8x2. We'll get negative 2x1 minus 4x2 minus x3, and we'll get negative x1 minus 2x2 plus 3x3. And if you want to take the composition backwards, we're going to take T sub 2 applied on T sub 1 of x, y, x1, x2, x3. And that would be the top, which is 2x2, x1 plus 3x2, and 17x1 plus 3x2. And there it is. Not that bad, really. All right. Again, a bit more practice on 16. If I look at this, I should know what the outcome matrix is for T1. That is 1, 2, 0, 0, 2, 1. Hopefully, we're really comfortable with that by now. The way it works, if you want to write it out, T1 applied on xy is simply x1 plus 2y, 0, and 2x plus y. And you would write that as 1, 2, 0, 0, 2, 1 applied on xy. So the matrix transformation for T1 is such. T2 of xy, again, you would really look at the outcome is going to be 0, 0, 1, 1, negative 1, 0, 0, 0, 1, and negative 1, 1, 0. If I'm not mistaken, let me double check all of those. So that one is a bit tricky, just a bit. And 0, 0, oh, 0, 0, 3, not 1, because there's a 3z. 1, negative 1, 0, 0, 0. Okay, 3 again, my mistake. And negative 1 for x, 1 for y. Okay, there it is. And again, you could write that out. You could say that is, look, that's 3z x minus y. So the reason I'm writing all of those, you need to be able to go back and forth between those. And when they talk about a linear transformation, you just need to know what that means. That's really the matrix 0, 0, 1, 1, negative 1, 0, 0, 0. Oh my God, let's turn with b and 1. And x first, negative 1, y, and multiplied by x, y, and z. Now, can I take T2, T1? Well, T sub 2 composite it with T sub 1. Again, composition happens to be T2, T1. Well, what would that be? T2 will be 0, 0, 3, 1, negative 1, 0, 0, 0, 3, negative 1, 1, 0. That is 4 by 3. And if I multiply that by 1, 0, 0, 1, 2, 0, 0, 2, 1. This is a 3 by 2, so the inners match very good. The outcome is 4 by 2. And I get 0, 0, 6, 0, 0, 3. For the second, I'll get 1 minus 1, that's just 1. 2 minus, that's only 2. And for the third is 0, 0, 6. And 0, 0, 3. And for the last entry, I get negative 1 plus 0 plus 1, that's negative 1. and negative 2 plus 0 plus 0, that's negative 2. There it is. Now if I go for C, I want to make that look, there we go. And there it is. If I want to take T sub 1, T sub 2, composite it, that is T sub 1, T sub 2. Well, that happens to be T sub 2 is, we're talking about 3 by 2, and this is 4 by 3. The inners don't match, so that's not defined. Definition, the dimensions don't match. Let me shift it. 18, they say express the equation in matrix form, then use theorem. Again, we're not going to use such terms on exams. We're going to say determine whether the operation is invertible. So what they're saying, hey, rewrite this as a matrix equation, the W equal A 2 negative 3 5 1 multiplied by x1 x2. So basically W is written as AX. That's really what you go for. Well, you look at this matrix and you figure out if there is an inversion. Let's see, yep, that one is invertible. That's not an issue. And if I wanted to find the actual matrix, I could have two things. I could either take 2 negative 3 5 1 1 0 0 1 and do the magic, or simply say, look, I have this shortcut. The inverse of A would be 1 divided by 2 plus 15. 2 plus 15 is 17. Swap the diagonals and multiply the 9 diagonals by negative, and that's simply negative 2 over 17, 5 over 17, negative 3 over 17, and negative 1 over 17. And that's pretty much it. If you ever need to find it, remember the theorem that we talked about last. To find the inverse of the transformation, you simply have to find the inverse of the matrix, and that's pretty much it. And that's your inverse right there. Now, your problem on the homework is a 2 by 2, but for me, I couldn't find anything other than a 3 by 3, so no problem. I worked it out on the side. I'm going to explain how this works. So here we're going to take this and write it as W1, W2, W3. Again, a matrix equation. 1, negative 2, 2. And 2, 1, 1, 1, 1, 0. Okay, so the standard equation, that's the word I was looking for. The standard matrix is simply the one I just found. 1, negative 2, 2, 2, 1, 1, 1, 1, 0. Now, determine the matrix operation. If so, find the standard matrix. What they want us to do, they want us to find the inverse of this transformation. And we're going to figure that out in a minute. Well, this is how we do it. We're going to take 1, negative 2, 2, 2, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. If I do the work and I get 1, 0, 0, 0, 1, 0, 0, 0, 1, what I end up with is 1 minus 2 of 4, negative 1, 2, negative 3, and negative 1, 3, negative 5. So if I wanted to talk about the inverse transformation, it would simply be W1 minus 2W2 plus 4W3, negative W1 plus 2W2 minus 3W3, and negative W1 plus 3W2 minus 5W3. That would be the transformation going backwards. And 24 is the last problem I want to talk about. Well, determine whether T sub A is invertible. If so, compute T sub, and remember how this works from the theorem that we looked at the last. It says if you want to take the inverse of a transformation, that's simply the transformation of the inverse of the standard matrix. So all what I have to do is figure that out. If it's invertible, then I'm set. Well, there's A right there. You know, I could write the whole thing. Well, I'm going to start with basically 1, 1, 0, 0, 1, 1, 1, 0, 0. And I'm going to work this out. And if I do that, then I'm going to get this to be so again, if I did the work 1, 0, 0, 0, 1, 0, 0, 0, 1, I'll get negative 1. Nope. I'll get 1 half, negative 1 half, 1 half, 1 half, 1 half, negative 1 half, and negative 1 half, 1 half, 1 half. So if you see this symbol on a test, that means I did the work and I gave you the answer. Show me how this works. So here we know that T sub A is invertible because that worked. Now just to remind you, if one of the rows zero out in any of those, then you say T is not invertible. And the inverse of A is simply 1 half, negative 1 half, 1 half, 1 half, negative 1 half. I'm just copying what I found right there. And let me double check those to make sure they're right. Yeah. So we say therefore the inverse of T is simply 1 half, negative 1 half, 1 half, 1 half, 1 half, negative 1 half, and negative 1 half, 1 half, 1 half, applied on 1, 2, 3, which is, and that will give me 1 half minus 1 minus 2 halves, that's negative 1 half, plus 3 halves, that's 2 halves, which is 1. I'll get 1 half plus 2 halves, that's 3 halves, minus 3 halves is 0. Negative 1 half plus 2 halves, that's 1 half. 1 half plus 3 halves is 4 halves, which is 2. And that will be the inverse transformation applied on the vector x. And there's our homework, and that concludes this section.